Electronics dominate the majority of the forms of storage we currently have. Technologies such as flash drives and memory cards make use of gated structures, such as transistors that store electrons between semiconducting materials. Larger forms of storage, such as hard drives, employ a technique where the individual grains of a metallic surface are magnetized in a specific orientation. Although highly efficient for memory needed to be read regularly, such forms of storage are prone to leaking, which over time becomes corrupted data. An alternative to storage that makes use of the actual structure of the material for storing information are polymers. Different monomers indicate different codes. For DNA, there are the four bases adenine, thymine, cytosine, and guanine. We also currently possess technology to accurately read and sequence DNA. DNA, however, being a biomolecule, has a short half-life. Synthetic polymers are much more stable in ambient conditions and are easy to synthesize. One such polymer is a polyalkoxyamide pioneered by Lutz and his team at the Institut Charles Hadron. Using an amide attached to a solid substrate as the alpha terminus, more amides are attached that, depending on their side chains, represent 1 or 0 in a binary code. Amides with 2 methyl groups represent 1, and amides with only 1 methyl group represent 0. Nitroxides are used as spacers between amides. The process is repeated indefinitely until you create a chain that contains the data you want. The mode of synthesis is amazing because it is iterative and orthogonal. The polymer can then be sequenced via tandem mass spectroscopy. Consequently, the same team, but this time led by Chloe Lowry, optimized the information carrying capacity of the concept by chopping off the polymer into distinct lengths so that the tandem MS graph contains more data per run. The former procedure has the advantage of ensuring sample homogeneity. You only expect one peak, but creating such long chains increases the risk of error in synthesis. The latter is more forgiving in correcting mistakes by just recreating the oligomer with the error, but analysis may require some time to sequence the oligomers and then sequence each chain found in the mixture. The researchers have already suggested some applications such as money anti-counterfeiting by embedding the polymer in the money. Packaging of products that need to be tracked down may be encased in a container made of the polymer. Lastly, the polymer may be turned into sheets that can store big data easily, instead of keeping servers that require a lot of electricity and cool temperatures. As for related patents, Intel has applied for the ultimate synthetic polymer barcode. It claims to have the capacity to attach a synthetic polymer backbone, probes, biomolecules, and even inorganic compounds and complexes to create programmable barcodes. It also claims to be read by simpler instruments such as FTIR and Raman spectroscopy. It follows the concept of using synthetic polymers as carriers of information, unlike other patents that use DNA. I also thought of my own novel ideas that were not stated anywhere. First, for the anti-counterfeit technology, the sequence-coded polymers can be embedded in the security fibers for an added layer of security. Even without sequencing the polymer, a normal MS graph would require a signature unique to the polymer mixture for the bill, which may be enough if tandem MS is unavailable. With less intrusive methods such as tapes, the design of the bill can be kept intact. Another application is by assigning barcodes to every person on the planet, and have all their IDs be embedded with the polymer sequenced with their own code. A card valid here can be easily authenticated in any other country as long as they have the barcode. It can be a form of universal verification. A limitation of the idea so far is that it requires tandem mass spectroscopy, which is a destructive analysis method, meaning the sample is lost forever in the process of reading the polymer. It is also expensive and not yet commercially available, only present in academic institutions and laboratories. Another point of improvement is that the process may be automated to produce polymers at a much faster rate than solid phase synthesis currently seen only in small scale, such as in the labs at CNRS.